Hello, so this is section 6.1, video number 1. We're going to leave the eigenvalues that we've studied in chapter 5 and explore the exciting new frontiers of the dot product and orthogonality in chapter 6. So this is our penultimate chapter. We've got a little bit that we're going to look at in chapter 7 after this, but yeah, so we've only got 2 more chapters to go. So, like I said, we're going to introduce a new operation called the dot product, which is defined on the board behind me. And then a majority of this section will be talking about a specific instance of the dot product, which we will define later on in this section. So without further ado, the dot product of 2 vectors u and v, each of length n. So to take the dot product of 2 vectors, the 2 vectors have to be the same length, is defined as u dot v. So if you see u dot v, that means dot product. This is technically, and you'll rarely think about it this way, but we define it this way because eventually we'll want to call this definition again later on in proofs. So keep this definition in your mind, but know that I never think about it this way. It's technically the matrix multiplication of u transpose in v. Because notice the transpose of a vector is just a matrix with a single row, right? And so now this product is just one iteration. I know I just did 2, but it's one iteration of the matrix multiplication dance, which turns out to just be u1 times v1 plus u2 times v2 plus un times vn. And so basically the way you take the dot product of 2 vectors, and this is the way I prefer to think about it, is you just line up all of the entries in the vectors, multiply the corresponding entries together, and then add each of those values you got. So let's see an example. So I've got 3 vectors here, u, v, and w. So by this definition, v dot w, to calculate this, I'm going to line up the first entry of v times the first entry of w, plus the second entry of v times the second entry of w, plus the first entry of v, or third entry of v, excuse me, times the third entry of w. And so this is 6 plus 4 plus 7, which is 17. So one thing to notice, the dot product of 2 vectors is always a scalar. Right? So we can see that here. We take 2 vectors, take their dot product, we get one number out. So I'm going to do this in 2 ways to introduce or sort of hint at a vector dot product property that we will soon see. U dot v plus w. So doing this sort of in the exact way, we get that this is equal to u, which is 1, 0, negative 1, dot 2, 1, 1, plus 3, 4, 7. And so I'll add these 2 vectors first. 1, 0, negative 1, dot the sum of these 2 vectors, which is 5, 5, 7, 8, excuse me. And so this is equal to, well, we match up the entries now, 1 times 5 plus 0 times 5 plus negative 1 times 8. So this is 5 plus 0 minus 8 equal to negative 3. But could we have done this in a different way? So while not technically being multiplication in the way that we kind of think of multiplication, it looking at this, I guess, product here, that we really should be able to distribute this u through this sum. And so we'll state this a little more formally in a second, but I want to convince you, at least with this example, that we can do this. And so that is that, in fact, this is also equal to u dot v plus u dot w, right, where I distribute u through each of these, through this sum, and so I take the individual dot products first and then add them up. So let's see if we can do it. So u dot v is equal to 1 times 2 plus 0 times 1 plus negative 1 times 1 and then u dot w is equal to 1 times 3 plus 0 times 4 plus negative 1 times 7. All right, so each of these individual sums, this is equal to 3 plus 0, 2 plus 0 minus 1, which is equal to 1. This is equal to 3 plus 0 minus 7, which is equal to negative 4. And sure enough, this is also equal to negative 3. So we've already sort of hinted at one of the properties I'm about to put on the board, that much like we can with multiplication, matrix multiplication, a lot of the properties we've been introducing thus far, the dot product can distribute across sums. And so as we'll eventually see and use this fact later on, the dot products can actually also distribute across multiple sums, or sums of more than just two vectors. And so we'll call that fact later on. But so we'll list this as a theorem. These are sort of the basic properties of dot products that we'll want to know moving forward. I think most of these are relatively intuitive, so I think for now, just to, in the interest of saving time, I won't give you proofs for these, except maybe for the last one, which will be very important. So if we've got 3 vectors, all of the same length, and a scalar c, then, as it turns out, it doesn't matter what order I take the dot product in. So the dot product of u and v is equal to the dot product of v and u. If you expanded each of these, you'd eventually see that basically these are just sums of multiples of each other. And since we're matching up the same ordered vectors in v and u, it doesn't really matter which order we multiply those pairs in. The second property is one we actually just saw. So u dot v plus w is equal to u dot v plus u dot w. And actually, as a quick sort of addition to this that I want to add, that we will use upcoming, if we have, say, u dot the sum of an arbitrary number of vectors, then we can distribute u in the same way. And this fact actually just immediately follows from this fact, but we will use the fact that basically we can distribute across a sum of an arbitrary number of vectors. That will come up later on in this chapter. So the next one basically says that if we've got a scalar and a dot product, we can factor the scalar out at any point. So if I've got the dot product of 2 vectors and a scalar c, basically what this says is I can multiply by c at any point in this process. So I could multiply c by u and then take the dot product. I could take the dot product and then multiply that by c, or I could multiply c times v and then take the dot product of that with u. Doesn't matter. All right. 4 is kind of the, I guess I wouldn't say most, well, 4 is the one that maybe will be most significant for this video. So the dot product of a vector with itself is always greater than or equal to 0. And in fact, the dot product of u with itself is equal to 0 if and only if, meaning the only time this happens, u is the 0 vector. So I want to briefly talk about this. Why is property 4 true? So to do this, I'm going to suppose we're going to look at, well, I guess we can let u be a vector of arbitrary length. So we're going to let u be the vector whose entries are u1 through up. I guess I said in Rn, so u1 through un. Then by definition, u dot u is equal to, well, notice the dot product of u and itself, I'm lining u up with itself and pairing off all of the same entries, right? So this dot product is equal to u1 squared plus u2 squared all the way out to un squared. So u dot product with itself, I don't know if dot product is a verb, but when I take the dot product of u and itself, I get a sum of a bunch of squares. Well, and of course we know that any number squared is non-negative, right? So greater than or equal to 0. So we know right off the bat that this number is greater than or equal to 0. But notice, each of these numbers is only equal to 0 if the original value in this vector was equal to 0, right? So u1 squared, so for example, u1 squared is equal to 0 only if u1 is equal to 0, right? But notice, if one of these values isn't equal to 0 and none of these values can be negative, then the only way this whole sum is equaling 0 is if every single vector in this sum is also 0. Or every, not vector, number in this sum is also 0. So as you can see, because u dot u is just the sum of the entries of u squared, u dot u is equal to 0 if and only if u is equal to 0, but even more generally, u dot u is always greater than or equal to 0. So keep this fact in mind. We will call on this fact actually in a very brief moment, because we're going to talk a little more about this specific operation. So I want to first look at a vector in R2 and try and see if we can have some sort of geometrical meaning for what the dot product of a vector in itself might represent. All right, so we're going to let u be a vector in R2. And so remember, maybe this is A, and this is B, then this would be our vector u. All right. So notice that u dot u is equal to a squared plus b squared. What if I wanted to find the length of this line defined by u? How could I do that? If I just had this picture and the knowledge that u was defined by the coordinate AB. Well, notice that if I imagine this line going up, I've got a right triangle there, and a side here with length A, and a side here with length B. And so by the Pythagorean theorem, the length of this side is equal to the square root of a squared plus b squared, which, as it turns out, is the square root of u dot u. One reason why we wanted to make sure that this dot product, because of course u doesn't necessarily have to be in the first quadrant in this picture, this dot product u dot u was always greater than or equal to 0, because for any vector, it turns out this is the length of the line defined by the vector. And while I used this example in R2, this actually holds for any vector in any dimension, Rn. And we'll say that the length, or this term norm is more commonly used than length, but these are basically mean the same thing, of V, which will denote double absolute value line V on either side, is just the square root of the dot product with V in itself. And so notice in particular, while again I used an example in R2 here, it turns out that you can actually do this with any vector in any dimension, right? It's just the square root of the sum of the entries squared gives the length of that vector, or the norm of that vector, I should say. So this was a fun problem that I wanted to give an example of. So this is a little like kind of those solve for h problems that we've seen, where we're going to be given this vector v in R2, x1, and we want to solve for all x. Nope, x is not a vector, x is a number, that make v have length 10. So what we want to do is we want to solve for this variable that's sort of embedded in the vector that make this vector a length 10 vector. So to do this, we just need to take our newfound formula for length. So we know that the length of v, which is equal to 10, is also equal to the square root of the dot product of v with itself. So remember, dot product, we line up the entries of v and sum their multiples. So this would be x squared plus 1 squared, which is just 1. And so this would mean that 10 is equal to the square root of x squared plus 1. And squaring both sides, we get that 100 is equal to x squared plus 1. And then subtracting 1 and taking the square root again, you'd get two values of x that give v a length of 10, specifically positive 99 and negative 99. So notice basically that the vector could be pointing one way or the other and have the same length. Yeah, so again, we'll actually look at an example in a second where we can apply this to vectors of higher dimension than R2, but I think R2 is a good example to see that the square root of the dot product of a vector with itself is the length, or as we'll start to use more commonly, called the norm of that vector. So one more note I want to make about this definition, and to do so I'm going to erase this example. This is sort of a property of norms that I want to quickly just state and then talk about the proof of. So for any scalar c, the norm of c times v is equal to the absolute value of c times the norm of v. And so in this way, we can kind of factor scalars out of, the norm. And what this is saying is that if I scale all of the entries of my vector by the same constant, right? So let's say c was equal to 2, and I double all of the entries in my vector, the length of my vector also doubles. So a quick proof of this, so if v is a vector of length n, whose entries are v1 through vn, then the norm of c dot times v, c is a scalar, so it doesn't make sense to talk about the dot product, notice is equal to the square root of c squared v1 squared plus c squared vn squared. Because of course, again, when we're taking the norm of a vector, it's the dot product of that vector with itself, which is just the squares of the entries in the vector. But if I'm multiplying this vector by c, then each of these entries also get hit with c. And so what we can do here, since there's a c squared in every single entry in this sum, I can actually factor out an absolute value of c out of this square root. And this is actually enough to give me this fact that I can factor out the square root of c. But notice, be very careful here. If I multiply v by any constant, I have to factor out the square, or the absolute value, sorry, not square root, the absolute value of that constant. This is, again, because whenever we're talking about length, which is ultimately what the norm of anything is talking about, length is never negative, right? And so even if the vector is pointing in the negative direction, length is never negative. All right, so there's one more thing, or one more idea, I guess, concerning this that will be very important in the next few sections. As it turns out, we really like vectors of length 1. There are a lot of reasons for this. 1 is a nice number to multiply things by because 1 doesn't actually inherently change any number when you multiply it. And we'll talk a little more about this in later sections, but because we like vectors of length 1, they have a special name. And so we say that any vector u with length 1, or with norm 1, right? So norm of u equal to 1 is called a unit vector. So I want to do one more example, because often with vectors, we aren't as much concerned with, and actually before the example, I'm going to draw an R2 because the example is going to be an R3, but it's hard to draw in 3 dimensions. And I guess like every stereotypical math teacher, I'm bad at drawing. So notice that I've got this vector v in R2. And often with vectors, even though we haven't, we've sort of expanded vector spaces to consist of a lot of different types of things, we really do care about the direction that a vector is pointing in, right? So here we've got v pointing in this direction, and maybe v has length greater than 1. Well, what we can always do geometrically, and I think this idea makes a lot of sense when you look at it geometrically, is find a vector of length 1 that is pointing in the same direction as v. Right, so here, this blue vector of length 1, we would say is pointing in the same direction as v. Make it a little more obvious there. Is pointing in the same direction as v. And, I basically, if v has length greater than 1, I just point a vector in the same direction as v that has length 1 until, or that, basically has length 1. So, this problem isn't terribly hard. The question might be, how do I calculate, what this vector should be? So I want to end with this example, but in R3. So we're going to let v be the vector 3, 4, 12. So first we want to verify that the length of v is not equal to 1. And so the length of v is equal to 3 squared plus 4 squared plus 12 squared, which is equal to the square root of 9 plus 16 plus 144, and 25 plus 144 is the square root of 169, which I think is equal to 13. So certainly the length of v is not equal to 1. But what if I multiplied v by 1 over its norm, so this was the vector v multiplied by the scalar 1 over 13. What would I get? Well, I'd get a kind of scary looking vector with a lot of fractions. But what if we took the norm of this vector? Well, this would be the square root of 3 squared over 169 plus 4 squared over 169 plus 12 squared over 169. We know the sum of these three numbers squared is 169, and so this is equal to 169 over 169, which is equal to 1. So what we just did is called normalizing a vector by dividing in its norm. And notice, again, since all I did was take v and multiply it by a scalar, I actually just got a vector in the same direction as v, right? Remember we had, so actually we haven't seen this yet, sorry. Basically, if I take a scalar multiple of v, it defines a vector in the same direction, but just not of the same length. And so this normalizes a vector. So the process of dividing a vector v by its norm is called normalizing v. The vector, and this is true for every vector v, v divided by its norm is a unit vector in the same direction as v. So if we have a vector whose length isn't equal to 1, we can just divide by its norm to get a vector pointing in the same direction whose length is equal to 1.